planet Earth is unique. An immense ball of rock, 25,000 miles around. It is a refuge. 1/3 land, 2/3 water, and with an atmosphere rich in oxygen, it is the only known home in the universe for living creatures. But this blue-green oasis has not always been so welcoming. The planet bears the scars of a traumatic past, a past of extreme environments and extreme catastrophes. Over the course of nearly 5 billion years, it has been a changing world. A world of fire, a world of ice, one of raging seas and poisonous skies. The life forms that now cling to its surface are the lucky survivors of a succession of deadly mass extinctions. For just over 200 years, determined scientists have explored the planet and unearthed its secrets. Their remarkable discoveries have led them to tell an incredible story, the story of how the Earth was made. For thousands of years, humans had no knowledge of the true age and origin of the world. But just over 200 years ago, all this would change. Scotland, the Edinburgh coast. It was here, one day in 1788, that the discovery of a small rocky outcrop would completely rewrite the history of the Earth. Geologist Geoffrey Bolton is on his way to the desolate Siccar Point, where this discovery was made by a maverick Scottish farmer, James Hutton. Hutton was to become the father of modern geology.
Hutton was a man who was enthusiastic in the pursuit of truth, a very inquiring mind. When he took over his father's farm, he saw underneath the soils rocks and wondered what these were.
Hutton spent years obsessed with understanding how the rocks of the Earth were made. His intrepid field expeditions took him all over Scotland, and they led him to realize that extremely slow processes could create the rocks he saw from layers of sediment.
He rode miles and miles on his horse to go places where he thought he could find exciting geological experiences, even though he suffered terribly from saddle sores.
Hutton concluded that rocks could take hundreds of thousands of years to form, but his claims were speculative, and his radical ideas flew in the face of the accepted version of Earth history, provided by the Church. For generations, the Christian Church had been the sole authority on all creation, based on the book of Genesis. And using the biblical genealogies, church leaders were now confidently claiming they knew the exact age of the Earth itself.
Archbishop Usher in the 17th century had calculated that the Earth was 6,000 years old, and indeed he calculated that it was made on October the 14th in the afternoon.
Hutton was convinced that the Earth had to be much older. And when his explorations led him to Siccar Point in 1788, he would finally find the proof he was looking for in the unusual formation he discovered.
These rocks are not just any old rocks, they're very special rocks, and the reason they're special is because of the story Hutton was able to tell from them.
Here, two layered rock formations stand at right angles to each other.
He knew these rocks had once been laid down horizontally on the sea floor. They must then have been buried under great depth to recrystallize. They must then have been tilted on end by great earth forces. Then they were eroded away and truncated. Then these rocks were deposited on top. And he realized that that would not take hundreds of years, nor thousands of years, but many millions of years.
Hutton's discovery was a turning point. From that day forward, it was rock, not scripture, that would become the trusted guide to the distant past. And over the next 2 centuries, the study of rocks around the globe would lead to the awesome revelation that this blue-green planet has been on the most astounding journey. A journey that began in a world of fire. It is now believed that the Earth was formed from collisions among the countless meteors that made up the early solar system. Back then, the surface was an ocean of molten rock, miles deep. Temperatures exceeded 8,000 degrees Fahrenheit, similar to the surface of the sun. And huge meteorites rained down in a relentless bombardment. The man who first proposed this hellish origin for the planet was the Victorian scientist Lord Kelvin. A British expert in thermodynamics, Kelvin believed that the Earth was slowly cooling down. The fires of the planet's interior, visible in volcanic eruptions, suggested to him that the planet had once been completely molten. Kelvin used thermodynamics to calculate a new age for the Earth. He reasoned that the molten planet would need nearly 20 million years to cool to its present temperatures. Kelvin was correct about the Earth being molten, but not about its age. His figure was a colossal underestimate. Like all 19th century scientists, Kelvin was unaware of a key source of heat inside the early Earth that prevented the planet from cooling as he predicted: radioactivity. In the early Earth, radioactive particles of uranium, thorium, and potassium were in huge abundance. The heat produced from the decay of these particles would keep the Earth extremely hot for an extremely long time. But although these particles confounded Kelvin's calculations, they would eventually prove the keys to unlocking the true age of the Earth. In the 20th century, rare particles of surviving radioactive uranium were collected together to create the first atomic weapons. But scientists had earlier found a different application, using the radioactive particles to accurately date the planet. In 1911, a gifted 21-year-old geology student, Arthur Holmes, used radiation to revolutionize our understanding of Earth history. After Holmes, geologists would talk in billions, not millions of years. Radiometric dating was simple in principle. It was based on the discovery that traces of the radioactive element uranium found throughout the rocks of the Earth decayed into another element, lead. Like sand trickling through an hourglass over hundreds of millions of years and at a steady rate, a sample of radioactive uranium will decay to lead. By measuring the proportion of uranium to lead in crystals trapped in ancient rocks, Holmes could accurately calculate their ages. Collecting data from samples from all over the world would be a lifetime's work. But as Holmes grew older, so did the Earth. Its calculated age extended first to 1, then 3, then finally to 4.5 billion years. Today, 4.5 billion years is still the accepted age for the Earth. Time on this incredible scale is known to those in the business as deep time.
It's difficult to imagine how vast deep time is, but think of it this way. That's a grain of sand. If it represented a year, then the length of my finger would be equivalent to the whole of my lifetime. From the tip of my finger to my elbow would take us back to the Pilgrim Fathers. From here to the rocky island you see on the horizon take us back to the age of the dinosaurs. And if we were to turn around and go to the equator, then it would be equivalent to going back to the beginning of the Earth, 4.5 billion years ago.
The search for the age of the Earth was over, and the results had opened a window on the past. For the first time, scientists could put rocks in the correct order, look deep into the Earth's past, and tell its story. They would discover evidence of an epic journey with many twists and turns. But the most significant step may well have been taken within just a few 100 million years of its birth, when the planet became a water world. $4.5 billion years ago, the Earth was formed from the collisions of millions of meteors in the young solar system. Temperatures were so high that the planet's surface was a molten ocean. But even at that time, Earth was beginning to cool. The radioactivity that provided much of the heat was slowly declining, paving the way for the planet's first radical change, its transformation into a water world. The Barberton Hills, South Africa. This remote region is home to some of the oldest rocks on Earth. South African geologist Gary Stevens is on the lookout for some of these incredibly rare survivors from the first billion years of Earth history, whose unique shape tells a story.
This area of South African geology here on the eastern side of Mpumalanga is critical for our understanding of early Earth processes.
Gradual erosion along the trickling creek can occasionally expose these primordial rocks.
Here we have an interesting rock. The rounded shape of this rock over here is very different than the rounded shape of the rest of the rocks in this river. This is one of these 3.5 billion year old pillow lavas. The rounded pillow shape in the rock is a result of the lava that formed underwater in an ocean approximately 3.5 billion years ago.
Pillow lavas are created today off the coast of Hawaii, where volcanic vents erupt into the Pacific Ocean. This unique pillow shape is only formed when lava solidifies under deep water. All rocks found from the period 3.5 billion years ago have been pillow lavas. By 1 billion years into the planet's existence, water had taken over. But geologists believe that it had already been around a long, long time. 4.4 billion years ago, the Earth was around 100 million years old. Meteors still crashed into the planet, but gradual cooling of the core had allowed most of the surface to solidify into a crust of dark volcanic rock. And even then, at this early stage, water was forming on the surface. No rocks now survive from this most early period, but tiny crystals of zircon do. Uranium-carrying zircon is one of the crystals that help date the Earth. But these crystals can also retain the chemical fingerprints of water molecules. And these fingerprints are all over the most ancient zircons. But the origin of the majority of the planet's water remains a mystery. As the planet cooled, the surface rocks began spewing out tons of carbon dioxide. Some water vapor would have been vented during this process, but some believe it would not have been enough to cover the surface.
The rocks, the material that accreted to form the Earth itself, would have been too dry, too close to the early hot sun. We have this problem of trying to understand where our water world got all of its water.
Impact expert Dan Durda supports the theory that the source of most of the Earth's water was extraterrestrial.
The idea today is that the Earth's oceans arrived from above. They were brought in the water-rich asteroids and comets which peppered the Earth during the tail-off in its accretionary process. What I have here is a piece of an actual meteorite. This is the material from which the Earth itself formed. This primitive little meteorite contains about 5% water. It's that water in objects like this that was delivered to the Earth to form the Earth's oceans.
Scientists are divided on this, but wherever the water came from, when it did arrive, it changed the planet dramatically. As it evaporated off the surface, huge amounts of water vapor rose to join the carbon dioxide in the young atmosphere, forming thick, blanketing clouds. This condensing water would trigger the greatest downpour the Earth would ever see. As thunderstorms rocked the skies, the rain began to fall on the rocky surface below. And it kept on falling. It would rain for millions and millions and millions of years. The result would be a water world. 4 billion years ago, the Earth was now 500 million years old. Over 90% of its surface had become a vast ocean. Small volcanic islands poked out from the waves. The monstrous seas were iron-rich, making them an olive green color. Carbon dioxide filled the skies so thickly that they appeared red. The dense atmosphere produced enough pressure to crush a human body flat. And it was hot. Temperatures exceeded 200 degrees Fahrenheit. This toxic, hostile water world would remain for another 500 million years. But dramatic transformations were on their way. Renewed volcanic activity would trigger the construction of the continents by creating a totally new kind of rock. Earth was about to become a granite planet. 3.4 billion years ago, the Earth was just over 1 billion years old. Huge green oceans dominated. None of the crumbling volcanic islands dotting the surface survived the punishing seas for long. But everything was about to change. An upsurge in undersea volcanic activity was about to create a tougher type of rock and give birth to the continents. In remote areas of the globe, the primeval cores of these first continents have been exposed. South Africa. Geologist Gary Stevens is climbing on some of the oldest continental rock on Earth. These rocks are special.
We're standing here on an ancient granite. This granite forms the nucleus of one of the world's oldest continents, and we can see it here in the Barberton area in South Africa.
These eroded outcrops of rock are the visible peaks of what is known as the Kapval Craton, a titanic mass of ancient granite underlying southern Africa, a remnant of the early Earth. 3.5 billion years ago, granite was appearing everywhere. An upsurge of volcanism had fractured the crust of the Earth underneath the vast oceans, allowing water to plunge into the cracks alongside the molten lavas. The mixture of superheated water and basaltic lava produced the new rock, granite. It rose from the depths to form the first true continental crust.
This is why granite is special and important. It's light. This rock, granitic rock, has a much lower density than this rock, a basaltic rock. The difference in density between these two rocks is greater than the difference in density between water and air. This rock would be typical for oceanic crustal material. This is typical of the continents. continents are light and buoyant, oceanic crust denser and heavier. It literally floats on the mantle.
Granite crust was not only light, it was tough. Tough enough to withstand the erosive power of the oceans. For the next couple of billion years, slowly but surely, the granitoid protocontinents grew larger. On different parts of the globe, granite crust appeared that would one day form the hearts of the major land masses. The dominance of the oceans was over. The continents had arrived. The slow expansion of the granite protocontinents was to change more than just the appearance of the planet. The shallow coastlines would bring life to the sunlit surface and help trigger the production of oxygen. Almost since the arrival of the first oceans, it is believed that primitive single-celled life forms had appeared deep beneath the waves, living off the heat produced by the subsea volcanic fissures. But now they were evolving and spreading upwards. On the continental coasts, an organism was appearing that was to transform the planet. The stromatolite. The stromatolite would live off sunlight, and it would fill the atmosphere with oxygen. This primeval organism can still be found today. Western Australia. Martin van Kranendonk is over 100 miles from the nearest town, heading across the outback to a remote beach.
We're going down this track to one of the most unique places in the world where you've got living stromatolites on the shoreline here at Shark Bay.
On the narrow sandy coast of Shark Bay, a multitude of stromatolites fill the tidal shallows. Each of these unusual rocky mounds are up to 1 foot across and 2 feet high. It was only in the 1950s that the importance of Shark Bay was realized. Following trips to this remote site, Australian geologist Philip Playford was the first to discover how stromatolites formed. Playford identified a rare bacterial algae found in a slimy film coating their surface as the creator of the mounds themselves.
Stromatolites are made up of very thin layers of microorganisms that build up slowly, layer by layer, year by year, as they use light energy to gain their food, and as their waste product, they precipitate rock.
Other geologists recognized the significance of Playford's findings. Patterns they had seen in rocks billions of years old were in fact fossilized stromatolites. Playford's discovery had sparked off a fossil revolution.
Once people knew that these kinds of structures were made by living organisms, they went back into the rock record and found that they found the same kinds of structures, and therefore could deduce that life occupied planet Earth 3.5 billion years ago. These are really the ancestors of everything on Earth. We're actually looking at our great-great-great-great-great-great-great-great-grandmothers and grandfathers.
The rock record shows that by 2.5 billion years ago, stromatolites were blossoming globally. All beaches on Earth would have resembled Shark Bay. And as stromatolites filled the shallows, they began to fill the atmosphere with oxygen.
Planet Earth in the solar system is the only planet that has an atmosphere composed of a large amount of oxygen. Geoscientists think that that oxygen came only from the reaction of stromatolites.
The algae turned sunlight into oxygen, a process known as photosynthesis. Over a period of 2 billion years, countless generations of stromatolites pumped out over 20 billion tons of oxygen. At first, the gas dissolved into the oceans, where it rusted out billions of tons of iron. But eventually, it would also fill the atmosphere and transform the planet. the planet's very appearance was dramatically altered. As the iron left the oceans, they changed from green to blue. When the oxygen moved on to the atmosphere, it diluted the remaining thick carbon dioxide and cleared the air. After nearly 2 billion years of oxygenation, the blue planet was born. The Earth now had its blue oceans and its blue sky. Relics of this great transformative period survive today in immense layers of iron-rich sediment originally deposited on the floors of the ancient oceans. Scattered all throughout the globe, the banded iron formations, as they are known, are vital for today's economies. They are the major source of all the iron mined today. Following its oxygenation, the Earth was more recognizable. But before it would become the planet we know, a new cycle of cataclysmic events would take place. Over the next billion years, deep movements would wrench apart the crust, and life, which had just begun to make its mark, would face its toughest test yet. $1.5 billion years ago, planet Earth was almost 3 billion years old. For the first time in its history, it was beginning to resemble the planet we know. Newly arrived oxygen had turned the oceans blue, and the continents had grown to cover nearly a quarter of the surface. But their expansion was not over, and beneath the oceans, deep forces were at work, rearranging their positions. Imperceptibly, the continents were on the move. Mark McMenamin is an expert in plate tectonics, the study of continental movement. Until the 1960s, this was radical science.
In the 19th and early 20th century, the consensus view was that the continents were fixed. All geology was local, and the continents stayed in one place.
But problems for this view had been mounting. One of the greatest mysteries was the geographic position of certain fossils.
Trilobites like the one on my left here belong to the genus Paradoxides.
The Paradoxides really was a paradox. It was a freshwater creature with a curious distribution.
This trilobite is found in the eastern part of North America.
And also in Britain, on the other side of the Atlantic Ocean.
The freshwater Paradoxides could not have swum the vast salty ocean. And they were not the only fossils showing bizarre intercontinental distribution. Geologists struggled for an explanation. In 1912, a radical new theory would emerge from Greenland that would lay the foundations for plate tectonics and shake Earth science to its foundations. The new theory was put forward by a German weather scientist, Alfred Wegener, a man who had spent much of his career conducting atmospheric research in Greenland's frozen wastes. But Wegener had always been fascinated by the geologist's fossil paradox, and he boldly claimed that the answer was staring them in the face.
Ever since accurate world maps were available, school children and others have pointed out the fit between the east coast of South America and the west coast of Africa, and this was always dismissed in reputable scientific circles as just a coincidence of no meaning, and so many disappointed children were turned away and told that their idea was wrong.
Wegener proposed that the continents had indeed once been joined together and had subsequently drifted apart. His observations in Greenland convinced him this continental drift was possible.
I think that his inspiration was meteorological. Perhaps he saw a breakup of ice flows and made what we would call an extrapolation to the hard rock part of the planet.
But few geologists could accept the radical theories of a mere meteorologist.
There was complete rejection of what Wegener was saying. This is a tall order to take a gigantic continent and shove it through the ocean floor to get it halfway across the globe.
Throughout his life, Wegener fought to gain evidence for his theory. But his brave attempts eventually led to his demise. In 1930, his last expedition to Greenland ended in tragedy when he lost his way in a snowstorm.
In an icy situation on a glacier, it's difficult to find your way. Separated from both his base camp and the other members of his expedition, he basically got lost and died of exposure.
Wegener was dead, but his theory of continental drift lived on. The breakthrough came after the U.S. Navy produced a global map of the ocean floor, originally commissioned for submarine warfare during World War II. This detailed map revealed one of the Earth's greatest secrets: the fractured network of submarine mountains, volcanic rifts, and trenches that split the oceans into enormous plates of crust. These plates would be the building blocks for the new science of plate tectonics. The rifts and trenches would provide a solution to how continents drift by proving that the ocean floors are continuously being recycled.
Plate tectonics is completely driven by the destruction of the old and the creation of the new.
Deep below the surface, mobile mantle rock is in continuous circular motion, following convection currents of heat generated deep within the planet. Where these currents rise, the rifts form and the plates are pushed apart, with new ocean crust created in the gap. Where the mantle currents sink back down into the Earth, they drag old oceanic plate down with them towards the interior. As the ocean plate moves, so do the continents.
That oceanic plate drags the continent along with it. The process is like an escalator or a conveyor belt.
The process of ocean creation is visible today on a rocky island in the middle of the Atlantic, Iceland. Iceland lies on the mid-Atlantic Ridge, a 10,000-mile-long range of subsea volcanic mountains that mark one of the deep rifts in the Earth's crust.
Iceland is really like a peak of this mountain chain. It's like a huge volcano sitting on top of it.
Seismologist Paul Einarsson studies the volcanism of this remote island, volcanism that is helping to expand the Atlantic Ocean. Occasionally, an unusual type of volcanic eruption on Iceland confirms the plate tectonic process. A fissure eruption. A fissure eruption is a wall of fire. They can be 25 miles long and spew lava hundreds of feet into the air.
People fear eruptions. They respect the volcanoes.
The fissures mark the path of the deep plate boundary that is creating the Atlantic. All across the island, running from northeast to southwest, are the remains of these fissure eruptions, scarring the rocky landscape with shallow canyons. These canyons are very slowly widening Iceland. At their base, new crust is being created, pushing Europe and America apart.
So here we are located in the fissure between the two continental plates, the two crustal plates. Here on my left we have the North America plate, and on the other side we have Europe. This fissure here is in a lava flow that's only about 8,000 years old. So in 8,000 years, that's how much the two plates have moved.
The rate of continental drift averages about 2.5 centimeters per year, the rate at which fingernails typically grow.
2.5 centimeters, 1 inch per year, means that in one human lifetime, America and Europe will move just 6 feet further apart. But over millions of years, this speed of movement was enough to shift the continents thousands of miles. Using plate tectonics as their guide, geologists such as Mark McMiniman have reconstructed the epic story of continental movement from the beginning. From samples taken from present-day continental margins, they've compared fossils and microfossils and matched up distinctive types of ancient rocks to reconstruct where the continents used to be.
It's a tricky task. It's kind of like Humpty Dumpty. You've got all of these pieces. You need to use whatever clues you can, whatever fingerprints you can, to put one continental margin against the other.
They are now confident that they can trace the movement of the continents back over 1 billion years to a time of a mass continental collision. As the oceans between them were swallowed up, the large land masses drew together in what was to become a supercontinent, Rodinia. It is believed that Canada and the USA formed the supercontinent's heart, with other continents bunched around them. But Rodinia was unlike any continent seen today. It was a desolate, lifeless place.
It would have been very much like being in the desert. It would have been similar to parts of the Sahara, Death Valley. There would have been no plants, no forests, no grasslands. Rodinia would have been a barren continent.
Rodinia may have been lifeless, but it was to have a profound effect on life in the oceans. In the oxygenated waters, primitive life forms were blooming alongside the stromatolites. But the huge supercontinent was about to give them a tremendous shock. Rodinia was to trigger what is now known as Snowball Earth, the biggest freeze the world has ever seen. By around 700 million years ago, Rodinia's position was blocking the currents that brought warm water from the equator to the poles. Without this heat, the polar regions froze. The resulting ice reflected more of the sun's rays away from the Earth, and in a catastrophic snowballing effect, temperatures dropped still further, and the ice advanced to cover the Earth. Surface temperatures fell below -40 degrees. The oceans were covered in an ice sheet almost a mile deep. The only life on Earth, marine bacteria and algae, were trapped beneath in the darkness. The result was disaster. All but a tiny fraction of organisms were driven to extinction. The whole planet was dying. $650 million years ago, climate changes triggered by the formation of the supercontinent Rodinia had left the surface of the Earth covered with a sheet of ice 1 mile thick. Temperatures hovered below -40 degrees Fahrenheit. Marine organisms, the only life on the planet, had almost been wiped out. The future of life on Earth hung in the balance. But beneath the ice, the supercontinent was in turmoil. Vast volcanic eruptions were splitting Rodinia apart.
It's thought that the accumulation of heat at the base of a supercontinent is what eventually leads to its undoing. It's like putting a blanket over the Earth. The heat that's generated in the Earth's interior will accumulate underneath that blanket.
The heat would spell the end of the snowball. As Rodinia ruptured, carbon dioxide released by the eruptions created a temporary greenhouse effect. The ice sheets drew back. Rodinia had broken into giant fragments, and the icy grip on life was broken. As shallow seas opened up in Rodinia's wake and oxygen levels increased, the primitive organisms were free to take their next great step forward. They would become complex and a lot more dangerous. The Canadian Rockies. These remote mountains are home to a rare record of this key event in the evolution of life, the so-called Cambrian explosion.
For the first time in the history of life on Earth, we have some of the highest oxygen levels that we've had since the Earth was actually formed. Life bloomed, and we see animals unlike we've ever seen before.
Paleontologist Paul McNeil is hiking up to a remote mountain quarry known as the Burgess Shale. The astonishing fossils in this quarry are a window on the world as it existed over 500 million years ago.
If you surveyed all the people who study the history of life, you get almost unanimous agreement that this is one of the most important fossil sites in the world.
The man who discovered the Burgess Shale was an American, Charles Doolittle Walcott, the president of the Smithsonian Institute. This fanatical fossil hunter, who was born into poverty, had lived the American dream. Armed only with a high school diploma, he had fought his way to the top of the American scientific establishment. But it was his tenacious fossil hunting expeditions in the most remote mountains of North America that would lead to his most stunning achievement.
This is the actual location where Walcott first made his amazing discovery. As the legend goes, it was August 31st, 1909, riding along this very trail with his wife in a snowstorm. And as they were riding along, a large slab of rock came down, blocked the trail, and they couldn't get by. Now, being a gentleman, as all paleontologists are, he immediately leapt off his horse, flipped over the slab of rock, and found an incredibly well-preserved fossil. If it was down on the trail, where did it come from? Nowhere but up there.
The source of the rock fall was a section of the cliff no more than 100 feet across. A small area that became the celebrated Burgess Shale Quarry. Walcott, often aided by his own family, eventually extracted over 60,000 fossils. And since Walcott, a further 100,000 have been excavated from this uniquely rich cliff face.
Quarrying the rocks out of the mountain requires a tremendous amount of work, a lot of back-breaking labor, but it's also extremely exciting because every time you split open a rock, you never know what you're going to find. Most of the time you find nothing, but every once in a while you find a new animal, one that's never been seen before, one that's been revealed for the first time in 500 million years.
The thousands of fossils found in the Burgess Shale revealed that starting 500 million years ago, life exploded with staggering diversity and complexity.
The preservation of these fossils is actually incredible in that they're actually preserved in 3 dimensions. You can excavate through the fossils themselves, see the internal organs, remove the organs, see the digestive tract. This is fantastic preservation. Oh, look, it's starting to crack, and there goes a piece. What we have here is an actual Anomalocaris. These guys were up to 1 meter in length. That actually made them the T-Rex of the Cambrian.
In the Cambrian seas, the oxygen-rich shallow waters were teeming with complex organisms. And creatures were feeding not just on plants, but on each other.
Cambrian is actually one of the most special times in the history of life. We see more different types of animals than we see in the rest of the entire history of life on Earth.
From this time onwards, with a biological arms race driving their evolution, creatures would become increasingly complex with the development of hard shells, skeletons, eyes, and teeth. Modern animals had arrived on Earth. The high level of oxygen that had triggered this explosion of life in the seas was also making a final modification to the atmosphere. Over the next 100 million years, oxygen reached today's high levels. A level dense enough to allow an ozone layer to form in the upper atmosphere. This layer was to free life forms from the oceans. Previously, powerful ultraviolet light would destroy any organism not protected by the water. Now, the ozone layer would act as a UV shield. "400 million years ago, the Earth is more than 4 billion years old. Over the next 100 million years, the continents would once again converge. And this time, thanks to the ozone shield, life was free to leave the oceans and conquer the land. Planet Earth had become a world of tropical swamps." South Georgia, USA, the Okefenokee Swamp.
The Okefenokee is believed to be what we would call an analog, a modern analog, or an environment that's very similar to the wetlands that existed on Earth in the past.
Fred Rich is an expert on prehistoric swampland. Geologists like him believe that this freshwater swamp closely mimics the surface of the continents 300 million years ago, in a period known as the Carboniferous.
The Carboniferous was an unusual time because it was the first period in Earth history when large plants occupied Earth's surface, 40, 50, 70 feet high, that grew in dense groves and produced a vast forest canopy in a steamy tropical jungle atmosphere that was something entirely new on the face of the Earth.
This dense tropical swampland would dominate the Earth for the next 60 million years. The evidence is present on all of today's continents in the form of coal. The coal we use for fuel was formed from millions of years' worth of accumulated plant matter, most of which existed less than 300 million years ago. And it formed because of the unique way freshwater swamps decompose.
Okefenokee is derived from a Native American word that means land of the trembling earth. It's not very easy to walk through the swamp because the subsurface is soggy plant remains.
The fresh water prevents the vegetation from decaying, allowing huge amounts to build up over time.
Beneath me is not the regular sort of soil that you would have in your backyard. The soil that you see here is the plant material that accumulated last year or perhaps 5 years ago. It's leaves, stems, twigs. There's still a good bit of water in this, but if we put this under tremendous amount of pressure and add some heat by covering over with layers of rock and leaving it in the ground for millions of years, eventually it will change to this. This is a piece of bituminous coal, and it's on the order of 200 million years old.
As the dead plants were transformed to coal on land, the shallow waters surrounding the continents were preserving millions of generations of dead marine organisms that would become our other major fossil fuels: oil and gas. Every year, mankind mines almost 5,000 megatons of coal, 30 billion barrels of oil, and 3,000 billion cubic meters of gas. This fertile period of Earth history has given us much of the energy we use today. Without it, the Industrial Revolution may never have happened. Plants were not alone in making a new life on the land 300 million years ago. As time went on, first enormous insects, then ambitious amphibians, and finally, early reptilians left the seas to take their first steps on the muddy shorelines. The U.S. East Coast back then would have teemed with monsters: 3-foot millipedes on land, 2-foot dragonflies in the air, and proto-alligators patrolling the nearby waters. The world was over 4.25 billion years old, and for the first time, the surface was host to a complete modern biosphere. But the all-conquering life forms were about to experience a hell on Earth. Forces deep within were about to give life on the surface its sternest test ever. Enormous volcanic eruptions would herald the biggest mass extinction in the planet's entire history. $250 million years ago. For hundreds of millions of years, life on the surface had faced numerous challenges to its survival, but nothing on the scale of what was about to happen. In what would one day become Siberia, the Earth's crust became a volcanic morass. The cause was a rare mantle plume eruption. No one knows for sure why they occur, but occasionally, huge masses of hot mantle from deep within the Earth surge upwards, melting and smashing the crust above. The eruptions continued for over 1 million years. They spewed out over 1 million cubic miles of molten rock, enough to bury the modern USA in a layer over 1,000 feet deep. Clouds of poisonous gases spread out and shrouded the entire globe. It was too much for most species of life. Over 95% were driven to extinction. It was the most cataclysmic event the planet has ever witnessed. The planet that emerged from the chaos was much changed. A new supercontinent, the great Pangaea, now dominated. And the climate was altering dramatically. Over the next 200 million years, oxygen and carbon dioxide would rise to new peaks. And under these conditions, the animals that had survived the extinction were to evolve into the most infamous creatures ever to walk the Earth: the dinosaurs. Utah, USA. Paleontologist Reese Barrick is on the hunt for dinosaurs. In this dusty corner of the western USA, the rocks are packed with their bones.
Almost a third of the history of life on this planet was dominated by dinosaurs. It really truly is a dinosaur planet. We have, from the bottom of this slope, sediments that are 150 million years, and as you go up the slope, you actually end up in the Cretaceous at 125 million years. How are we doing, Barb?
Doing great.
Find anything fun?
A small rib and some interesting fragments.
Well, that's a start for the day.
Compared to modern creatures, dinosaurs were enormous. The average mammal today is smaller than a dog. The average dinosaur was larger than a grizzly bear.
Marvin, excellent. Look at that. That is a spectacular therizinosaur claw. This animal's gonna have to be 300 kilograms, so it's about the size of a National Football League lineman. These are absolutely fantastic because they are very well-preserved bone. A perfect claw. Absolutely brilliant, Marvin. Nice job.
The first recorded dinosaur fossil find was a bone discovered by young Mary Ann Mantell in England in 1822. Her husband, Dr. Gideon Mantell, was intrigued and set about determining what type of creature it belonged to. The fossil was unlike anything he'd ever seen. After much research, he decided it was in fact a tooth from an enormous lizard. He named the beast Iguanodon, after the iguana lizard he thought it resembled. Over the next few decades, across Europe and the USA, more and more huge bones were unearthed, and given their similarity to modern lizards, the name dinosaur, meaning terrible lizard, was coined. But many paleontologists today believe one of the reasons dinosaurs grew so large was that they weren't cold-blooded like today's lizards. They were lukewarm-blooded. This gave them the advantages of both cold-blooded lizards and warm-blooded mammals.
Dinosaurs were able to be active and collect food all year long, and yet they could put a great amount of the food that they ate towards growing as opposed to just heat generation.
But another reason for their size may have been the sweltering, oxygen-rich environment that came to dominate the dinosaur era, an environment triggered by volcanism. Starting around 180 million years ago, a new upsurge in volcanic activity split apart the supercontinent. The continental fragments began their long journeys into the positions they occupied today. North America, South America, Africa, and Europe all went their separate ways. The Pangean supercontinent was no more. Each of the new continents still carried dinosaurs, and the steamy volcanic climate seemed to suit them. It was global warming gone wild. CO2 levels increased over 500%, and temperatures soared. In the greenhouse conditions this created, huge tropical forests spread across many of the continents.
The increasing amount of tropics meant that there's a lot more lush vegetation, which means there's a lot more food for dinosaurs, which allowed them not only to specialize and evolve to specialize on different types of plant materials, but allowed them to get extremely large.
Many scientists believe that evolving for millions of years in this warm, oxygen-rich world allowed the lukewarm-blooded dinosaurs to reach their enormous sizes. Huge dinosaurs may have been a biological response to a volcanically overactive planet. But size would not save the dinosaurs from what was to come. Their time on Earth would end in sudden, unstoppable devastation. $100 million years ago, planet Earth was ruled by dinosaurs. huge beasts filled the land, the sea, and the air. They lived in a sweltering world defined by overactive volcanism. And before it was finished, this volcanism would bring to the surface some of the planet's most wondrous riches: diamonds. Kimberley, South Africa. Jock Roby is chief geologist at De Beers, the largest diamond company in the world.
Diamond is simply the high-pressure form of the element carbon. This is a typical 8-sided crystal called an octahedron. Uncut, it is worth $2,000 a carat. As a cut stone, it would probably sell for $80,000.
For thousands of years, diamonds had been found worldwide washed up in sandy riverbanks, but their source had remained a total mystery. It was not until 1869, when huge, unique diamond discoveries were made in South Africa, that their remarkable origin was revealed.
What is special about the diamonds found in the Kimberley area was here for the first time ever, they found the source rock of diamonds. This is a piece of rock mined from the kimberlite, and as we turn it, it contains a diamond.
The diamond-bearing rock was extracted from strange vertical formations.
As the miners were digging, they found that the diamonds were contained in a body of rock that had a shape of an ice cream cone, slightly broader at the surface, yellow in color, tapering down to a narrower point.
Henry Carvel Lewis, a visiting American mineralogist, put together the pieces. He realized these diamond mines were actually the mouths of ancient volcanoes. The miners were digging down into their roots through the diamond-bearing magma that remained. But these were clearly not normal volcanoes. They were over 3 times deeper, extending nearly 100 miles beneath the surface of the continent. Uniquely intense pressures and temperatures at this depth make it the only place that diamonds can form. And the diamonds could only be brought up by uniquely intense eruptions. The diamond-bearing magma exploded out of the earth at over 300 miles an hour.
Imagine the force and the power of this volcano to cut those sheer vertical walls and blow this up another 1,000 meters. This is the power of these volcanoes.
When the Pangean supercontinent split apart over 100 million years ago, scientists believe the enormous upheaval triggered these super eruptions. Because supercontinental breakups are rare, so are the diamonds they bring to the surface. The diamonds that erupted into the dinosaur world would survive unblemished until the present day. But the dinosaurs would not be so lucky. "65 million years ago, the planet was lush. Vegetation was thick on the surface. Living things were prospering like never before. But the dominant dinosaurs were about to be wiped from the face of the planet."
Dinosaur bones are found continuously throughout the sedimentary record from 230 million years ago right up to 65 million years ago, and then instantaneously they vanish.
Not only dinosaurs, but over 70% of species on Earth disappeared. From plant life upward, something terrible had happened to the entire ecosystem of the planet. This mass extinction remained a mystery for generations of paleontologists. But it is a mystery no longer. Colorado, USA. Dan Durda is taking samples from an exposed layer of rock exactly 65 million years old. Scientists now believe that it holds the answer. For Dan Durda, this powdery rock is an indication that the dinosaurs perished in a sudden astronomical catastrophe.
Dinosaurs and 75% of all the other plants and animals that live with them, this layer is their tombstone. This thin layer of clay is the important evidence of a violent event in the history of life on the planet.
The evidence held in the tombstone layer is a huge amount of an exceptionally rare element, iridium. The remarkable concentration of iridium was discovered accidentally in 1980 by a father and son team of scientists, Luis and Walter Alvarez. On the planet's surface, iridium is usually found in very small concentrations. Most of this rare element originates from space rock, deposited from the multitude of small meteors vaporizing in the upper atmosphere every day. The Alvarezes were looking for variations in the strength of these tiny meteor showers, but when they realized this huge concentration was held in the infamous tombstone layer, they proposed a radical new theory for the extinction: death from above. The dinosaur planet had been hit by an enormous meteor. Their theory remained controversial for over 10 years until the final piece of the puzzle was discovered in Mexico. A hidden crater over 100 miles across.
In 1990, the Chicxulub impact crater was discovered, and its age, when finally dated, turned out to be precisely 65 million years old. It was the smoking gun for the Alvarez theory.
Worldwide, the tombstone layer contains an estimated 200,000 tons of iridium. This translates to a meteor over 6 miles in diameter. Its impact on the planet would have been devastating.
You've got to imagine Mount Everest flying at you across the sky at 20 kilometers per second. Several thousand cubic kilometers of the Earth's crust were vaporized and excavated and launched around the entire planet, slowly raining back down through the atmosphere to settle across the surface of the Earth as a thin layer of dust and debris.
But the meteor was not alone in wreaking destruction. Today in India, ancient lava flows exist that are so thick, whole temples have been carved into their layers. The lavas were the result of a massive eruption that was occurring simultaneously with the meteor strike. Although not as extensive as the earlier Siberian eruptions, these lava flows in western India could have buried the USA to a depth of over 600 feet. The huge clouds of toxic dust they produced would have rivaled those of the meteor. 65 million years ago, the meteor impact and the eruptions would have been a deadly double blow. Whichever had the stronger effect, the combination of these events sounded the death knell for the dinosaurs. The dust cloud lingering high in the upper atmosphere and blocking the sun devastated the life below. The huge dinosaurs, along with most other major species, were extinct. The new world that was to follow would be the world of the mammals and the world of man. 50 million years ago, life was slowly recovering after the cataclysmic extinction that obliterated the dinosaurs. The Earth had been around for over 4.4 billion years. But only now were the first mammals, our ancestors, beginning to flourish. Long before humans arrived, the continents continued to move and crash into one another. Slowly but surely, the surface started to look familiar as plate tectonics and erosion created the dramatic landscapes we see today. The Swiss Alps. Some mountain chains can be explained by volcanic eruption of rock from the depths of the Earth. But the greatest including the Alps, contain no volcanoes. They appear to have risen as if by magic up from the plains beneath. This famous range runs through the heart of Europe and reaches over 3 miles above sea level. How was such a huge mass of rock pushed up so high? Adrian Pfiffner is an expert on the structure of the Alpine chain, and he knows the answer.
The scene we see in front of us is the result of a collision between two continents, the African continent and the European continent.
A close study of the Alpine rocks can provide clear evidence of how the mountains were formed. The secret is revealed in quartz crystals that are extremely small.
These slices are about 25 thousandths of a millimeter. At that thickness, you see through one single grain.
The tiny crystals in the rock reveal massive deformation.
The quartz grains have been really stretched, elongated and flattened. You need large stresses in order to deform these rocks. One process that is doing this is actually the collision of two continental plates.
For the last 45 million years, as the continents have continued to move, the African plate and subplates have been grinding into Europe. The continental crust along the collision point experiences extreme pressure, and the solid rock itself is warped and buckled.
If you assume that my hands are two plates which are squeezing the rocks in between, you can see that some of the material escapes upwards and leads to the building of a mountain chain.
The twisted folds of the rock strata are exposed as the mountains are slowly squeezed higher and higher. One famous alpine mountain demonstrates clearly this collision of the African and European continental plates. The Matterhorn. The Matterhorn is the child of two continents.
What's amazing about the Matterhorn is the top pyramid of the Matterhorn is a piece of Africa, and it lies on Europe.
In the formation of this classic mountain, the two continental plates have actually overlapped.
You can think of a car crash. If two cars crash with each other, maybe one car slides over the other one. The two continents moved together, and Africa moved on top of Europe.
Plate tectonics are responsible for all the Earth's mountain ranges. And over millions of years of growth, the only thing that has stopped them grinding inexorably skywards is erosion. Erosion by snow, wind, and rain.
This is the action of water that is eroding the mountains. Now this might seem to be something very small, but actually if you look at the entire Swiss Alps, 50 million tons is eroded every year, and this corresponds to a small mountain roughly 1,000 meters high, one every year.
The height of mountains around the world are determined by these two opposing forces, uplift and erosion, changing them by fractions of an inch up or down each year. But plate movement and water erosion can also create the opposite of a mountain. Under the right conditions, the surface itself can be cut away, sometimes spectacularly. The Grand Canyon, over 1 mile deep, 10 miles wide, 277 miles long, and still growing.
One of the great stories of exploration is when the first Europeans saw the Grand Canyon in the year 1541. And a couple of those men came over to the rim. They saw the river down below and they thought it was 6 feet wide. the explorer, sent a couple of his men down, and they came back later and said the canyon is deeper than it looks.
Wayne Rainey is an expert on this geological phenomenon. Its unique scale, the consequence of titanic forces of nature. Over the course of the last 6 million years, this spectacular canyon has been carved by the slow, winding Colorado River, in combination with dramatic uplifting of the Colorado Plateau. Plate tectonic processes have pushed the whole plateau upwards. It now lies over 8,000 feet above sea level.
This uplift probably occurred with the Pacific plate coming into the North American plate and wrinkling the crust, much like if you took a throw rug on a hardwood floor and pushed it along the hardwood floor. When the edge of that rug reaches the wall, you'll see this big bow up in the rug, and that's exactly what's happened to the western edge of North America.
The river looks too small to cut a canyon so deep, but its height above sea level means that the force of gravity gives it great power.
All you have to do is look at big rivers like the Amazon or the Mississippi. They have much more volume of water than the Colorado River does, and yet they don't cut large canyons because their landscape is not elevated. So uplift brings the rocks into an elevation where the river can then saw down through all of those layers and create the canyon landscape we see today.
Plate tectonics combined with erosion have sculpted many of the features on the surface of our planet. And as a general rule, the most jagged, tallest peaks and the deepest canyons are the youngest of these grand structures, all formed within the last 50 million years. But the final touches have been added by yet another major force of nature. 2 million years ago in East Africa, ancestors of modern humans were taking their first steps on Earth. At the same time, down from the North Pole, enormous icy glaciers began to descend. The Earth was about to enter the Ice Ages. Two million years ago, ancestors of modern humans had begun to spread out of Africa. But the Earth around them was cooling down. Before long, much of the planet would be coated in huge glaciers. The Ice Ages had arrived. The grand freezings were triggered when overflowing volcanoes in Panama created the land bridge joining North to South America and radically altered global ocean currents. The polar seas cooled significantly. The result was that pronounced dips in global temperature could now tip the planet into ice ages lasting tens of thousands of years. Iceland. The Löngjökull Glacier. In the highest, coldest parts of the planet, glaciers still reign supreme. Few venture out in these hostile terrains, but glacier climatologist Finnur Pálsson and his team regularly battle the freezing elements.
When you're doing glacier fieldwork, conditions can be very bad.
Outside, it is below minus 20 degrees Fahrenheit.
I like to work in harsh conditions. Difficulty is something you need to tackle.
Finnur is keeping tabs on the growth of the glacier. At present, it is over 350 square miles, the size of New York City. And although it may look static, in fact, it is in constant motion. Glaciers are formed initially by snowfall on high areas. The compacted ice is then dragged down by the force of gravity. The glaciers move like slow-motion rivers.
You can think of ice as soft material like toothpaste. It flows. If you would make a big blob of toothpaste on a plate, it would slowly sink down and flow away to the edges.
Finnur and his team in Iceland regularly check on the incremental movement of the ice.
This is a satellite positioning system. We can calculate the position of this point with an accuracy of about 2 centimeters to calculate how fast the glacier moves.
Finnur's measurements tell him that this glacier is moving at over 150 feet per year. In today's mild temperatures, glacial advance is kept in check by glacial melting. But if global temperatures were to drop by just a few degrees for a long period, then the glaciers would grind slowly forward and the Earth would enter another ice age. The existence of ice ages was first discovered by 19th century Swiss geologist Louis Agassiz. As he explored the Swiss Alps in the 1830s, Agassiz couldn't help but notice the immense boulders scattered over farmland and the bizarre towers of gravel capped by stones that stood guard over some of the mountain valleys. To explain how the rocks arrived at these positions, he speculated that they had been carried and deposited by ancient glaciers that had once filled the alpine valleys and covered the northern hemisphere. Initially ridiculed by his peers, Agassiz's Ice Age theory became accepted as telltale signs that these huge glaciers had indeed covered the continents were found all over the globe. The evidence is everywhere. New York's Central Park. This oasis of green in the middle of Manhattan exposes part of the island's ancient bedrock. Many large outcrops are visible, and they contain the footprints of the glaciers. Climate expert Jörg Schaefer is looking for subtle traces of this frozen world.
It's actually something I bet that most New Yorkers do not know. You see the ice ages everywhere if you open your eyes.
Look closely, and the super hard bedrock is marked with scores of tiny parallel lines, fractions of an inch deep.
So this point here is actually one of the most amazing spots of evidence for an ice age in the middle of New York City.
The grooves were caused by small rocks caught under the massive weight of a moving glacier.
These little rocks basically cut like a knife into this very hard bedrock. This is clear proof that once an enormous ice sheet was moving in this direction in the middle of New York City.
The glaciers that hit New York were massive. They rolled down from the Arctic and buried Manhattan under a huge depth of ice.
To give you an idea about the thickness of the Laurentide ice sheet in the Manhattan area, it was at least twice as thick as the Empire State Building is high today.
Over the last 2 million years, as the climate fluctuated, the huge ice sheets waxed and waned. With every pass, they gouged and crushed and reshaped the land beneath them. As the last glaciers retreated 10,000 years ago, they left behind a bruised and battered landscape and created features we still see today. In the USA, Cape Cod and Long Island are built on immense piles of boulders dropped from the retreating edge of the North American ice sheet. And the great weight of the ice formed huge depressions that now make up the Great Lakes. In the warmer climate that followed the last glacial retreat, early humans had free reign over the surface. In this brief period, a fraction of 1% of the history of the Earth, the entire history of human civilization has taken place. Human ingenuity has reshaped our planet. From our perspective, our achievements are breathtaking. But will we continue to survive and prosper?
Humans have, with technology, dominated the planet more completely than perhaps than any other animal in the history of life. But we've done it for such a short period of time that we've got a long ways to go.
Over the past 4.5 billion years, the Earth has been on the most incredible journey. Over the eons of its existence, the planetary environment has undergone immense transformations. And since the arrival of life, these transformations have in many ways determined which organisms will survive and which will be swept aside. If this turbulent past is any guide to the future, life, and humans in particular, will face further battles for survival as the planet continues along its path of change.
Life is highly dependent on the Earth. What the Earth gives us is what we have to deal with.
It's hard to separate completely the processes of geology and the processes of life. Life, in some ways, drives geology, and geology creates the environments in which life thrives.
Our first major challenge will be the climate. At the start of the 21st century, we may worry about global warming, but most scientists recognize that we are in a gap between ice ages. Our whole civilization has occurred in a brief warm period, 10,000 years so far. This warmth has proved crucial.
It's definitely not a coincidence that civilizations developed over this period of time, because the climate is so favorable to our species to develop and flourish. The period we live in the moment, climate-wise, over the last, let's say, 10,000 years, is exceptionally stable. It's almost unbelievably stable if you look into the geological record. It certainly will not stay forever like that.
Even if our industrial economies affect a global warming over the next couple of centuries, they can do no more than delay the inevitable. The continent's current positions, keeping the polar oceans cool, mean that in just 15,000 years, a new ice age may occur.
The New York area is going to be completely changed by the next cycle of glaciation. And at some point, glaciers are going to move down and grind New York into the North Atlantic Ocean.
But even if we survive the big freezes, there will be greater challenges to come. As plate tectonics move the continents and end the ice ages, coastal regions will be engulfed and whole countries will disappear. 200 million years from now, a new supercontinent, Pangaea Ultima, is due to take shape, as first the Mediterranean and then the Atlantic Ocean are swallowed up.
There will be continents eventually colliding with the east coast of North America. So New York, in the long run, will be destroyed in a continent-to-continent collision and will be completely crushed and thrust upward as a new mountain range.
The Earth will once again be thrown into deadly turmoil. Oxygen levels and surface temperatures could fluctuate wildly and lead to new mass extinctions. But even the trauma of supercontinental disruption is nothing compared to what will follow. Everything will grind to a halt when the plate tectonic engine finally stops.
The maintenance of habitability on this planet is involved with the plate tectonic cycle. It's not an infinite cycle. There is an end in sight. It's billions of years from now, but we know eventually the system will wear out.
The fires in the depths that have dominated activity on the surface will one day use up their fuel, and the story of planet Earth will be over. Without its burning heart, the Earth will share what many believe was the fate of Mars. The atmosphere and oceans will be stripped away, and the surface will become a bone-dry, barren desert. The planet will be dead. But this is a picture of an incredibly distant future. For at least the next billion years, as the Earth continues its epic journey, some form of life should continue. But the human species, which have walked the Earth for over 2 million years and mastered it only in the last 10,000, may be endangered. As the environment transforms, Earth could well become unfit for humans. If that happens in the distant future, rather than be forced to face extinction like our predecessors, technology may allow us to leave Earth in search of new homes, other blue-green planets on which to make a new start, leaving planet Earth to continue its amazing journey without us.